Thank you for coming. It's nice to see you all. It's really fun to be here at the University of Chicago. It's my first time, and it's been great. So I'm going to talk a bit today about disorderly programming and some experiences, and then some theoretical conjectures, maybe if we have time, from my group's work. This is a smaller crowd than this talk was sort of designed for. It's kind of like a big band thing, and maybe this room should be more like a quintet. So if it's not working, let's just stop and talk, all right? Because with this smaller group of people, I don't know if I should do my props and all this kind of thing. So we'll see. We'll try it. So I figured with that kind of a name, I couldn't resist doing anagrams. So that's the other version of the talk title. And it actually, you'll see that it's very relevant to the talk. So there's another name for the talk. All right. So as I was introduced, I grew up here in the Midwest. And when I come home, I think about my childhood. So I'm going to tell you some childhood stories to motivate my work. One is called Urgency, and the other is Resurgency. And these are unfinished stories, and you get to decide maybe at the end of the talk which of them you think is how to finish these stories, let's just say. I'll give you a sense of kind of the intuition behind what I mean by disorderly programming. I'm going to do a language primer that's going to, for those of you who haven't seen logic programming, kind of step you through it. For those of you who have, review it or perhaps embarrass myself at how elementary and poorly presented it is. But I'll try. And then, if we have time, some of the implications and conjectures. So, motivation. The first story is the urgency story, or what is sometimes called the programming crisis. And this story is the story of Chicken Licken. So many of you who are Americans, anyway, probably know the story of Chicken Little. This was a British edition that I had as a kid, and they call it Chicken Licken. And my mom was kind enough to scan it for me. So I always like to thank my mom at this point in the talk. So I thought we'd read the story together just to refresh our memories, even though many of you know it. So it goes like this. Once upon a time, there was a little chicken called Chicken Licken. One day, processor clock speed stopped following Moore's law. And instead, hardware vendors started making multi-core chips, one of which fell on Chicken Licken's head. You know what happens next, right? The sky is falling. The sky is falling. Computers won't get any faster unless programmers learn to write parallel code, squawked Chicken Licken. Henny Penny clucked in agreement. Worse, there is cloud computing on the horizon, and it requires programmers to write parallel and distributed code. I would be panicked if I were in industry, said John Hennessy, then president of Stanford University. This is from an interview in ACMQ. Many of his friends agreed, and together they set off to tell the funding agencies. So it's a true story. It's a very scary story. You may remember the end of this from your childhood. It ends with Foxy Loxy, right? So this is a very distressing children's story. The next story I want to tell is a very happy story, a very sweet story. And if you're a fan of the British series of Ladybird books, which apparently they are such fans because there's a whole Flickr group of book covers I was able to find. So they're actually really cool, sort of weird popular culture thing from the 60s in Britain. So this book is really pleasant and boring. It's called Springtime for Logic, and it goes like this. In a faraway land, logicians and database theoreticians had reason for cheer. Declarative logic languages like crocuses in the snow were cropping up in fields well outside the walled gardens in which they were first sown. Another true story. Many examples of logic programming were blossoming. Security protocols, compiler analysis, natural language processing, probabilistic inference, modular robotics, multiplayer games. And in a patch of applied ground in Berkeley, a small group was playing with Datalog for networking and distributed systems. The Berkeley folk named their project Boom, short for the Berkeley Orders of Magnitude project. The name commemorated Jim Gray's 12th grand challenge from his Turing Award lecture to make it orders of magnitude easier to write software. They also chose a name for the language in the Boom project, Bloom. So those are my two unfinished stories. And you can try to decide as you get to the end of the talk whether you think it's more about doom and gloom or boom and bloom. Okay, so that's my little introduction. And it's time for me to give my intuition on disorderly programming. But I had to pause because you guys were such wonderful hosts. I arrived yesterday. I drove up from Champaign-Urbana. It was a perfect day, so I went to Millennium Park. And I saw the signs that you had put out for me. They're all over the park. It had these signs. And even in my font. And I thought, my God, you guys are all class. This is just great. So it's really...
It's hard to change the font. I got to tell you, we had to go
yeah, see? So thank you so much. It touched me. I sent, obviously... I'm sorry?
It's just this Midwest font.
It's the Midwest font. That's right. Very good. So I sent off the pictures to my group right away. We were really happy. So let's look at this doom and gloom thing. And why is it considered so hard? Why does John Hennessy, who's a very smart guy, see this as such a big roadblock? All right, let's go kind of first principles on that. Well, programming is hard. And in fact, Jim Gray's Turing Award speech, 1999, at that time, he was talking about the cost of single processor programming was too expensive, and he wanted that to be orders of magnitude cheaper. And he felt that was an intellectual challenge on the order of the Turing test and building the memex and things like this. So he listed that as the 12th of his dozen grand challenges for computing. That was before parallelism was being presented to us as a requirement. Okay? Well, parallel programming is harder, and distributed programming is yet harder than that, arguably, because it's parallelism plus failure and latency. And these are things that, with multi-core and cloud computing, we're going to have every programmer needing to do. Okay, so this really is the reasons for the doom and gloom and the crisis, they're real. So let's go kind of think about where they come from. And this is, getting back to the title of the talk, Mad Men, I can't remember what it was, something Grizzly Rigger. A lot of computer science and programming comes out of von Neumann machines. So what's a von Neumann machine? It's this reference architecture where you have this ordered array of memory as your fundamental data structure, and you have your ordered list of things to do, okay, as your logic. And this is the way that Fortran works, certainly. And it's kind of the way that we think about programming and the way we teach it. Programming, an algorithm is a recipe, right? First, you break the eggs, and then you mix them with the flour, and then you do this, and then you do that. And it's based on this notion of really ordered behavior over ordered things, all right? And this clearly is a bad idea when the world is a world of multi-core machines, and there's many of them, and you're trying to harness them all at once. It's very inefficient and complicated to write a program that maintains order over these things, okay? And that's why it's so hard to auto-parallelize code that was written with the assumption that you have orderly behavior. So, getting back to the title of the talk, Mad Men, drop Grizzly Rigger. This very rigorous ordering of programming as our fundamental basis of programming is a bad fit to modern computing. And this reordering challenge that parallel computing's been looking at for all these years is really hard. And so what I'm advocating is something different, which is disorderly programming. Why don't we teach programming, and why don't we do programming where our fundamental data structures are unordered, and we start with that, and our code is unordered as well, okay? And then that, unfortunately, would not maybe be expressive enough. I'll come back to that. So help the programmer put in the order only where they need it in their programs. And part of this message here is there's this saying that programs that are easy to parallelize are embarrassingly parallel. That's an accepted term in parallel computing. And I would say there's no reason to be embarrassed by that. In fact, we should use it and build on it. So we're going to start with the stuff that's easy to parallelize, and then we'll enrich the language with constructs that allow us to be more computationally complete, and we'll try to keep the programmer from having to use them when they don't need to. So the default is going to be disorderly. So here's how we do this. At an intuitive level, our basic data structures are no longer arrays. They're disordered things like sets and bags, multi-sets, okay? And our programs, how do we make code disorderly? Well, here's one take on it that's been popular, is data flow, or if you like in software these days, MapReduce. The idea is you have a list of things to get done, okay? And they're in order, but the things you're going to do, each one of them is a big job, and you can spread it across a lot of things, okay? So we have a whole bag full of x's. Massage each x. That'll keep you busy for a while. And when you're done with that, massage each y. And when you're done with that, match up the massaged x and y's. And when you're done with that, count up the matches. Right? And this will be easier to parallelize because there's lots of x's and there's lots of y's, and they're disordered. Right? You don't care what order you deal with them. That's good. The following is better, which is logic, which is we're just going to write down a set of things we want to know at the outcome. All right? And you'll notice that we don't have to know them in any particular order. We're just going to write them down. I'm going to assert to you I have some x's and some y's. Call R a set of massaged x's, S a set of massaged y's, J a set of matches between R and S, and C is the size of J. Now I can write these sentences down in any order I please, and I haven't said anything about how to evaluate them. All right? So there's no imposition here in this program, in any case, of any need to do ordering. And you may disagree with me about that, and we'll come back to that point soon. But this is the theme of it, is we're going to write down in some sense what we want, not what we should do.
I mean, J is the set of massaged X, R, and M matches. So there is an implicit ordering that you have to get R in order to match.
Indeed, indeed. There are data dependencies implicit in these sentences. Right.
Okay.
The programmer isn't telling you how to respect them. But computations will have intrinsic orderings. Okay, but we're not going to over-constrain because we haven't said anything about what to do. We've only said what we need. Yeah, but that's very astute. Very good point. And I'll go a bit further, which is to say that for Turing completeness, sometimes we do, in fact, need to explicitly order things. This comes out of descriptive logic, actually, which we were talking about earlier, and that is indeed the case. And what we'd like to do is take a program that's all disorderly and run it through sort of a debugger and have the debugger detect points of order and say, hello, I'd be very happy if you'd like to inject a little more logic here for coordination that will make sure that these things happen before those things happen. And I can do that for you automatically, or maybe you know something about your code that I don't, and you can feel good about not doing that. OK, so this is kind of the high level. We'll dig into details in a bit. Before I do it, I used to give talks that were more about what we had built. And this talk is much more about the language we're designing based on our experience building things. But I want you to get a sense that we built a whole bunch of real stuff in this style. And we did. So this is actually over about 7 years, I was surprised to find, since we started doing this. So we started by building web crawlers and peer-to-peer network crawlers in this style. Okay, and then we had the idea that those looked awfully like the routing protocols that the internet works on. And so we proposed and implemented the design of network routing protocols in a logic language. So all these things are done in logic languages, distributed logic languages. We implemented higher-level overlay networks, like the chord algorithm, if you're familiar with that, in a logic language. I then had a student who was building embedded SensorNet code on these very small devices with only a few K of memory. He built a whole software stack in this style in logic, so from the radio media access layer all the way up to the application layer and everything in between. And he did a bunch of network caching and proxying work there. We rebuilt our own systems in our own language. So our query optimizers for our language were built in our language, and that includes dynamic programming algorithms as well as query rewriting algorithms. I got interested in machine learning and distributed machine learning, and we implemented a number of those algorithms in our language. Then more recently, we've been looking at distributed systems, classical distributed systems. We looked at classical consensus algorithms from that community, like Paxos and two-phase commit. Again, in the machine learning space, information extraction algorithms in recent years. The biggest stuff we've built is we took the Hadoop file system, which is a widely used distributed file system. It's used at Yahoo heavily. It's used at Facebook very heavily, and a bunch of other companies. We took that code, which is written in Java. We rewrote it from scratch in our logic language. Our code was orders of magnitude smaller, and then we were very quickly able to add features to it that the HDFS system doesn't have and desperately needs, like avoiding a single point of failure. It's a little scary to realize that, or maybe not surprising to you to realize that Facebook has single points of failure all over the place. And then we also hacked the Hadoop job scheduler to be declarative, and we were able to do all sorts of scheduling policies. Yeah?
So programs are written to be run, but they're also written to be read.
Sometimes, yeah.
I tell my beginning programmers that they should write their programs to be read.
Good.
So you've written all this stuff. Are you going to tell us about how to think about organizing these statements so that it's coherent and understandable?
I'm going to give you a glimpse of it. We're still in the midst of that, I would say. But what I'm going to do is show you the syntax we've been doing doing this as an embedded language in Ruby. So you'll see you may not see here without further discussion, but you'll see that we've been able to take advantage of built-in things in Ruby like inheritance and encapsulation and stuff in concert with these kind of programming styles. But I wouldn't say we've figured out the right way to do that yet. But that's the stage we're at, actually, is making this a real programming language and not a logic syntax. We're in there. We're fighting that battle now. So it's great. Great question. So I think a fair thing to say, especially in response to that, is with some struggle, the people who are designing the language were able to build these things, orders of magnitude smaller and orders of magnitude less time than the people building it in Java professionally. Is the code production quality? Maybe not. Is it very readable? Depends on the beholder. Let me give you a data point, however, which is important, and it gives you a sense of the scale. Our chord implementation, well, the MIT chord implementation, which is the reference implementation, is about 10,000 lines of C++. Our implementation is 47 lines in our language, and you can print it on a single piece of paper. Okay, so we can argue about whether our code is stylistically well designed and so on, but the point is you can sit down at the coffee shop and you can kind of get it in cache in your brain all at once, which you just can't do with 10,000 lines of C++, no matter how nicely written. Okay, so the orders of magnitude has something to do with that.
So you just mentioned, I don't know, 4 or 5 features of a language that are all of interest, but one that was noticeably absent was efficiency.
Yeah, I'm not going to talk about that much today. Which is funny, because I'm like a systems guy, and that's what I was trained to do. One of the reasons we're not doing multi-core, and we are doing cloud, is cloud is a setting right now where people are writing really inefficient programs anyway. If you look at these Hadoop and MapReduce systems, they're terrible pieces of software. They're not very beautifully written, for one thing, but also they're really, really slow, and a lot of those are architectural decisions to make them slow. Let's favor fault tolerance over speed. Let's favor simplicity of the fault tolerance over speed. So we didn't feel too bad about performance. We did make sure that like this stuff, since we had real reference implementations, was within a few percent performance. So we did some experiments on our HDFS, and it was like 10% off of native HDFS. It's not really much of a bragging point, though, because HDFS is not a very efficient system. But Yahoo doesn't care, and there's partly because they're nuts, frankly, and partly because it doesn't matter that much. Google cares, actually. They iron out their performance much more so than Yahoo and Facebook. The other thing I'd say is, performance comes over time. We'll get there. It's not a first-order problem for me. I think we'll be good at that. So the take-home message we were trying to sell with this stuff was orders of magnitude less code in most of these cases, 10 to 100 times shorter programs. And again, my story is not that we have 6 less lines than you, but you can read our code in one sitting, and you couldn't possibly read that code in one sitting. So that's the scale that I care about when we talk about lines of code, is orders of magnitude. In some cases, like the sensor network routing code, we were able to show that because you said things at a high level, we were able to optimize. And we'll get a flavor of that as we go in the talk. Bad thing from this experience was these were languages that were mostly declarative. And then we had to stick in some imperative stuff to do things like state update. And it was icky. And it kept tripping us up. And we'd do things like, oh, this program doesn't work. Let's change the evaluator for the language. Oh, good. OK, now it works. Now that program doesn't work. Because the specifications of the program somehow entailed details of the evaluator that were not really well visible in the language. And so we were very unhappy about this, and one of the things we've done since then is get the next 10%, so it's fully declarative now. OK, so let me take you through some of this, give you a sense of what these languages look like, give you a sense of the language I'm trying to design now, what Bloom is going to look like, and get some feedback, because it's absolutely a work in progress. And see how that goes. So this is a funny section of the talk because it's parallel lecturing. So you have to do parallel listening. So I've tried to do 3 things at once here. For those of you who don't know logic programming, I'm going to step through a primer on logic programming or a review. I want to give you a sense as we go, and this will sneak up on you, hopefully in a positive way, that logic and distributed programming fit together very well. That there's some things about distributed programming that are sort of inherently about logic, and also that you can express distributed programming in logic languages. But that's a syntax thing as far as I'm concerned. And then the third thing is that familiar design patterns in your normal programming language, like Java, we can call them logic, and you wouldn't even know it. You'd think you were programming in Java. Okay, and so I'm going to try to convince you that I can sneak this into your diet without it tasting bad. All right, is sort of the goal. And you'll see that that third thing is kind of at odds with the first 2 things. So the first 2 things are really about talking about logic programming. The third thing is about pretending it's not there. And when I talk to programmers, I'm trying to talk about number 3. All I'm trying to do is help your life. It doesn't matter that it's logic programming. I'm just trying to make programming easier. But since you're not most programmers, I'm going to tell you about the stuff behind it. Okay? So here's the world of computing from a database geek's point of view. Okay, so what is the world of computing? It's data and logic. That's all there is. What is data? Well, you can think of it as things stored in collections, preferably unordered data. And then there's logic, which is the stuff you can deduce from the data. All right, so for instance, here's a Datalog statement. If you know Q, you know P. It's sort of a propositional Datalog statement. If you know SQL, but you've never seen Datalog, an SQL view is the same thing. It says, I'm going to have a query over some table Q, and I'll name that query P, and from now on I'll pretend it's a table, even though it's not. Okay? And those are the same thing. Those are both logic. Okay? And this is all of computing, and when I say it's all of computing, I mean it. Like, you can have a Turing-complete language in this style, and I do. Okay? Until recently, nobody cared unless they were like a European theoretician in the programming languages community. Okay, but as I said in my little story, in the last decade, this stuff's been cropping up all over the place in applied computing settings. People who are not interested in Datalog, they're not interested in the language per se, but it was the right tool to use for program analysis or for dynamic programming in machine learning or for what have you. Okay, so it's coming back, right, kind of on its own. We weren't coordinating when this was happening, and frankly, I hated Datalog in school, so I'm not happy about this. And because I hated it, you have to suffer too. So here's how I learned it in school, all right? So this is the classic example you'll find in your database theory textbook from Jeff Ullman in 1982 or whatever it was when it first came out. And I think you'll still find it today. You have a relation called parent of pairs x, y, where x is the parent of y. All All right? And then you have rules that say things like, if xy is in parent, then xy is in enk, where enk is the ancestor relation, and they insist on calling it enk. All right, which leads to stupid puns in my paper about having a lot of enks. And then if you know that xy is a parent relation and you know y is an ancestor of z, then you know x is an ancestor of z. All right, so that's it's like an inductive statement about what's an ancestor. And here's an example. This is the family tree of IBM mainframes. And here's an x, a y, and a z. So now we know x is an ancestor of z if y is an ancestor of z. Okay. And then there's this syntax which everybody should love, which is capital letters are variables and lowercase letters are constants. That's very readable. Okay, and you can ask a query like this. Put a question mark at the end and you say, for the constant s, find me all ancestors x. Okay, so you can ask queries in Datalog in that way. So a couple notes on the language. Variables are in caps, constants in small case. As a rule, if a variable appears on the left-hand side of the deduction operator, all right, and that means this is called the head and this is called the body. That means this variable is getting its values from something over here. If one of these variables over here isn't over here, it means it's getting its values from the universe, which is all possible values. We don't like that. Okay, that would be what's called an unsafe query. So we're going to have a rule, if something's over here, it has to be over there. All right. Scopes our variables to something with a finite number of bindings. And then the other thing to keep in mind is these predicates, parent, ancestor, which you could call tables, predicates, relations, they have no duplicates. They're sets. Okay? So if you deduce something you already knew, that doesn't change anything. All right. Final piece of terminology, be careful here. This y and this y are the same. It's reuse of this variable. It's trying to say, in SQL terms, the second field of parent equals the first field of ancestor. That should be true of all the matches. All right, so this variable matching is how we line up the matches between these relations. And that's called unification in logic programming jargon. And this is really important to the programmer. So think about having a table with 27 attributes and another table with 34. And you write down an x over here and an x over there. They better be in the right places. Okay, so the third field of that and the 17th field of that, that's what we're trying to match up. It's really terse and really compact. It's a lousy syntax. Okay, it's horrible to debug. All right, so I had to learn this many years ago, and it's old and boring. And of course, since then, everything's changed. So the internet changes nothing at all. So this is network routing on the internet, all right? So it's the same exact thing. Instead of ancestors and parents, now we have something useful like neighbors in a neighbor table on a node, which we'll call link, and paths in the internet. So this is the program that computes, all paths to S from other destinations. Same kind of thing. Recursion on graphs is not like something that you only did in the 80s. Right? It's a pretty basic construct. All right, so I want to take a minute to talk about semantics. How many people have programmed in logic programming languages at some point in their life? Okay, and how many people have taken a logic class in the math department at some point in their life or taught one? Okay, yeah, so I would kind of not have raised my hand for either of those things. I did take a logic class. It was really hard, so I guess I would have raised my hand. But let me give you a little flavor of kind of how these people think, for those of you who aren't one of those people. So this is, for a logician, this is just syntax from some grammar. Okay, and it doesn't have any meaning. It's just syntax. And if you want to assign it meaning, that's nice, good for you. And we can call that meaning a model. And the meaning we're going to have is substitutions for the variables with tokens. Okay? And a reasonable model is a set of substitutions that is consistent with the rules. Okay? So if I give you a set of links to start with as our stored data, a model would be a set of paths that goes along with those links and is consistent with these rules. All right. Now, I might say I have, as my stored data, the roadmaps of the Earth. Okay? And you might say that a consistent model is all paths on the Earth plus flights to Mars. Right? And that would be consistent with all the roads on Earth. But you would have added flights to Mars, which is sort of random. All right? So let's agree on a sensible model, which is the minimal model. It's the smallest number of paths that are consistent with the links you have. Okay? So the minimal model semantics is one nice canonical interpretation of this program if you want to give the syntax some meaning. Okay? Make sense? Minimal model? So here's a cool lemma about Datalog programs. Simple Datalog programs always have a unique minimal model. So not only can we agree on a decent meaning, but we can agree on the one meaning of this program. It's the unique minimal model. So that's nice. So now we have a program that is just a syntax, all right? But we have an interpretation of that program that means something that we can all agree on. Even better, if you're a computer scientist who likes to do stuff, there's a natural execution strategy, or really a family of join algorithms and join orderings that will compute that minimal model using a very simple strategy. All right? And as I say, the strategy is parameterized. So really you get to optimize. You get to choose one of many execution strategies from a family that I guarantee you will produce that model. All right? It's this very simple strategy called semi-naive evaluation is the one we use. It starts with the facts like links. It generates paths, and then it combines paths and links to generate more paths, and it keeps doing that until it can't find anything new. That's called a fixed point. The fixed point of that execution is the minimal model. So cool. So now we have this thing. It's a beautiful mathematical object with no meaning. We have a meaning for it we all agree on, and we have a way to translate that to an algorithm that can compute it. This is pretty. This is nice. Okay? Yay. Good. And then this guy comes along, and maybe he's already in the room. All right? And he says, yeah, cool, dude, but I'm not actually going to write like programs like that. So I want to spend a little time trying to convince you that this is not esoterica, okay? And that I can satisfy this guy too, okay? This guy's real profile picture on the web, so, you know, he did it to himself. So suppose you like Java. Here is my path program. This tiny little program in Datalog. Here's what it looks like in Java, more or less. And what I've done here is I've said collection types in Java. Do they have them? Sure, they use iterators. Okay, so we'll have an iterator for links, and we'll have an iterator for paths. And the first rule, which says make sure that if something's in link, it's in path, will be expressed like that. Go through all the links by doing next on the iterator. All right, and for every link, add it to path. Okay, and here we're going to go through the links and the paths with, unfortunately, a nested for loop, which sort of suggests an evaluation strategy. Okay, so you for each link do path. That's a little bit ordered, right? And then we'll find all the pairs and stick them into path again. Okay, but you know, I could look at this program and say, hey, I can reorder the for loops. I can even get rid of the for loops. I can interpret this syntax as basically that. All right, so if you want to program in for loops, cool, man. You know, I'll let you program in for loops. Maybe we can boil down Java to just the for loopy kind of things that correspond to logic. And you'll never know the difference. You'll program in Java or a subset of Java, and I will be able to do all my cool logic stuff with it. So the reason I use Java here is twofold. First, many people think it's a real language. Okay, and it looks horrible. Okay, I mean, this shouldn't look that yucky. Okay, so here's the syntax of the little language I'm building. So this is the version 0 of Bloom, which I call BUD, which is an acronym for Bloom Under Development. Okay, and it's a domain-specific language in Ruby. So this has all been implemented. This language is actually just a sublanguage of Ruby. So all this is good Ruby that I'm writing here, and it parses and runs in the Ruby interpreter. And so here what I'm saying is, take the link collection and do a map on it. That is to say, for each L in link, output the pair L from L2. And for the moment, interpret that symbol as stick it into, and stick it into path. Okay? And then I'm saying the same thing here for, I'm calling it join because I'm a database guy, all link path pairs, L comma P. If L.2 equals P.from, form that output and stick it into path. All right? So you may disagree, but I would argue that that's a pretty normal syntax for a programmer. It's not that crazy. They probably might have an operational interpretation of it, of like, go through all the links, go through all the maps, stick them together, test them, and shove them in the other side. But it's just logic. It's just this. It's a syntax for this. OK, so parallel lecturing. We're going to keep going on our example. So I want to make the example more interesting. The example before was just finding reachability on the internet. All pairs of nodes where from one you can get to the other. That's not really that helpful. I want to know how to get to the other, and maybe how much it'll cost me to get from here to there on the internet. So let's change our program a little to do that. We'll add an attribute C to the link table, which is the cost of a link. So it's the latency, let's say, the average latency or the expected latency of the link. And we'll augment this rule now to say we'll pass the costs into path, right? So if x, y, c is in link, then x, y, and c will be in path. We're going to add another variable to path, which is the routing information, OK? It's the next hop on the path. So if you want to get from x to y, the place you go next is y. OK? So that's how we build one-hop routes. And now recursively, here's the interesting part. If you know that that xy is in link with cost c and yz is in path with cost d, then let's say that xz is in path with cost the sum of the two. Okay, and for next hops, well, let's be a little bit careful. We know to get to z, we transit through n from y. To get from x to z, we're going to transit through y, and then to n, and so on, right? So that's why there's a y here for the next hop. And that's my little program for forming paths. Okay, why did I show you that? Well, for one reason, I wanted to show you that I'm extending the language. So I cheated here. This is no longer just Datalog. This is Datalog with function symbols. I got a plus sign. What is a plus sign if you're a logician? It's a ternary relation of C, D, and E, such that E happens to be the sum of C and D. All right, that's a model for this predicate. It's all triples such that the third thing is the sum of the first two. It's an infinite relation. It's a big, big table. Okay? And when you have infinite relations, the expressive power of the language increases. And you have to be careful that the outputs of your programs are not infinite. All right? And there's some conservative tests for that work pretty well. We'll call those programs safe, the programs that have finite models. And we'll just assume we can test for safety of programs. It's usually true. OK. But still, that's not what we wanted in internet routing. I don't want all paths on the internet. That's insane. I want only the shortest paths. Okay, that's how routing really works, for some definition of really. We're going to get realer and realer as we go. So let's do best paths. We saw these rules before. We're going to add some extra rules to get the best paths only. All right. So for each pair xz, this is a syntax we made up in a version of Datalog we called overlog. For each pair xz, I want the minimum cost for that pair, which is going to be defined as take the path relation and for each xz pair find the minimum c, all right, where y is dropped in this example. So if you like in SQL, this is select minimum c from path grouped by x comma z, if you're an SQL person. Okay, so that's what that's doing. Now we've got triples of source, destination, cost, but we don't have paths. So we need to put it all back together, which is to say take all the paths. For those paths from x to z of minimum cost, matches here, put those in the best path output. Okay? So now this expresses to find just the best paths. Okay? And now you can ask queries like this one. For a particular source, what are the best paths to every destination D? Right? And that's, in fact, what you want to know in internet routing. This is what BGP computes. All right? And this gets stored at node source.
Can I just ask a question?
Yeah.
It seems it would be more efficient if you only compute best paths and not all paths.
Who said I computed all paths? This is purely declarative. So until you query this relation, I'm not going to compute it, let's say. And if you only query this relation, then maybe I don't need to compute it, which is maybe your point. Isn't there a nice way to compute best paths that avoids computing all of path? And the answer is yes. Yeah, good.
You get nice results,
You do, in fact, yeah. Well, it depends on how you optimize the program. So we're going to see this in a bit.
Can I ask you a question?
Yeah.
So if your graph has a cycle,
Yes.
then you have an infinite number of paths.
Always true. A problem in network routing, page something of the networking textbook, yeah.
So how do you deal with that?
I didn't in this. It's another line. Okay, it's the same way that you find in the networking thing, which is you look for cycles as you go and that kind of thing. So you would write a rule where you'd project away the costs in the left-hand side, and you check for a min and that kind of thing. It's easier if you assume that your paths are always positive. Otherwise, you have to run around, right? Yeah. Okay. Good. Language feature alert. I just added another language feature, which is aggregation. This is a biggie, okay? Because aggregation is non-monotonic logic. So stop for a minute if you're going to nap through parts of the talk. This is a good part to wake up on because the rest of the talk won't make as much sense. Non-monotonic. So a logic that is monotonic is one in which when you introduce new axioms, if you like new facts or new rules, all right, the model gets bigger and bigger. Okay. So that's nice. The more data I put in, the more facts I get out. The more I know, the more I know. Very good. Non-monotonic logic is one in which the introduction of new axioms can make things that were true in one model be not true in the model with the new axiom, in the program with the new axioms, right? Aggregation is like that. So think about a scenario where you say, if the count equals 0, then I know something is true, all right? Well, that's fine, but if you introduce new things, the count may no longer be 0, and that thing you thought was true is now false. Right? So your model just shrunk. So that's non-monotonic reasoning. It's the source of lots of discussion in logic programming literature. We're going to use it for a very particular analysis property, which is endemic to computing. Okay, but you should know what it is. And any aggregation, typically what they check for is count equals 0, which is also usually expressed as set is empty or just not of set, not true set. Okay, so that's the typical example of non-monotonic logic. But anything that does aggregation, like mins and max and countsies and all that stuff, all right, those are non-monotonic as well. I introduced that in the language. It increases the expressive power of the language. Assume that we're doing the following. Whenever you see a non-monotonic predicate, like min cost, its definition is predicated on the full set of its inputs. So this thing, if you like, is evaluated only when I have all the paths. Only then can you say which is the min. All right, if you want to think of it as being computed. If you want to think of it as being defined, this is the minimum over all paths, right? And you need to have all paths to define what this means. So you need to close the world of paths. This is one way to do it. They talk about the closed world assumption. You need to say, there will be no more axioms. This is my complete set of knowledge. Now I can compute aggregates. Okay, so kind of yucky. Here's how it looks in Bloom. Take all the links and stick them in path. Form the join of links and paths, and for each LP pair in that, stick it in path. And then I introduced an argmin syntax into Bloom. So instead of that awkwardness of finding the shortest path for each pair and then combining it with all the paths to find the path that has the shortest cost, I just write that in one go. I say in the path relation, find the path such that it has the minimum for each from to pair of cost. Okay, and that's best paths in Bloom. And again, I would argue, unless you haven't seen argmin before as a sort of a construct, and you don't have to use it, this mostly looks like something a programmer might be able to deal with. Okay, so getting realer with our program. What have we got so far? We have this like logic for finding shortest paths. It smells like a routing protocol. But I'm assuming there are these facts. They're in some like database in the sky. Like where are all these facts and where is this computation happening? People have proposed that the right way to do internet routing is to have a service that computes routes, like the Google of finding routes on the internet. And that's not the way the world works. Right? The way the world works is that the various internet service providers run a distributed protocol to compute paths, which is BGP, the Border Gateway Protocol. So can this way of programming lead to distributed protocols? That was my goal in the first place. The answer is yes. What's fun is that it happens in the dumbest way you can think of. That does the trick, which is we're going to partition our tables physically by row-wise. Okay, so in database terminology from the 80s, they call this horizontal partitioning because you take the table and you slice it this way into rows. Okay, MapReduce works this way too. You take the records in MapReduce and you give some to some machines and some to other machines. Okay, the way we're going to partition the table is we're going to hash with the identity function on some attribute of the relation. So one attribute of the relation will have an @ sign in front of it. We'll call that the location specifier. That's where you look in the tuple for an address. And the address you find there is where the data should live. Okay? So data placement is based on the location specifier. And this kind of whole point I'm making now is the basis of the P2 system and the overlog language, which if you're in the systems community, many people know about. That was one of our more visible papers. So let's take our protocol and put it on a network. Here's a network. It's got 4 nodes, A, B, C, D. Here's our link table that's been distributed with the @ sign on the first field, which is the from field. From to, or source field, if you like, source destination. So we'll see that links outside to go away from A are stored at A, links outbound from B are stored at B, links outbound from C are stored at C, and so on. And that's what that says. Okay, and these are base facts that are stored as the routing tables on these nodes, the neighbor tables, I should say, on these nodes. Now, we want to compute routing tables, which are paths. So this is our first rule. We induce this part of the path relation from this link relation in the obvious way. And note that it's all local. Every node did this itself. And you can see that syntactically because both of these are partitioned by X. All right, so you know that you can compute that without communication across nodes. This rule, unfortunately, you can't compute without communication across nodes because I want to unify on Y. And link is not partitioned by the destination field. It's partitioned by the source field. So for example, I need to put together, oh, yeah, there you go. I need to put together these two records. I can get from A to B, and I can get from B to C. But those two things are at different nodes. So communication is going to have to happen to put them together. So the way we'll get this communication out of this program, we'll do what logic programming people like to do, which is we'll do it syntactically. We'll rewrite the program to get what we want. Okay? We'll generate another program, which is going to be equivalent, but do what we want. And, oh, by the way, the facts have to go back home to @x, right? So that's part of what we need to get the rewrite to do. So here's the rewrite. We call it a localization rewrite because it's going to make the program run locally, at least in the right-hand side of the rules. We're going to rewrite that third rule to these two rules. The first is a rule that takes things in link and it sticks them in link underscore D, but link underscore D is partitioned by the destination field. Okay, so it has the effect of taking this tuple and copying it, copying it over there. Okay, so if you're in link over here, you're in link D over there. And the next thing we do now is if we look at that, that's the rest of link D. If we look at this rule, Now it's partitioned on the same attribute that it's being unified on. So we can do all the joins, if you like, locally. All the matching can happen at a single node. Right? And send the result back to the X field of the output. Okay, so we shoot the results back to where they go. So that's the trick. That's very nice, whatever, kind of cute. The fun thing about this, which follows on to your question, is this is the distance vector protocol that's used in BGP. Right? And they describe it very operationally as a node shall emit advertisements about its routes, and then the advertisements will receive responses about extensions to those routes. And it's kind of described as a protocol. But really the way I view it is I had a declarative specification of these path tables I wanted and how I wanted their outputs distributed. I didn't say how to get the data where I wanted it. I just said at the end, paths should be stored at the sources, and links should be stored at the sources. Right? And here's what paths and links combine together to do. This was one way of implementing that, and it's the way that this rewrite popped out. I could instead have shipped paths to links. Right? I could have repartitioned path so that it was partitioned the same way as link and done it that way. That would have given me a protocol called dynamic source routing, which is a wireless protocol if you're a networking person. And so the argument here is, the networking community kind of bottom up was thinking about different protocols for different physical scenarios, where really the outcome was the same. And when you're in an environment like we have today on the network, where there's so much differentiation and variation, what's wireless, what's wired is not so important. What you want to do is tune the protocol to the performance parameters you're in. Right? You want it to optimize itself. So you want the high-level specification, and you want the optimization into something else to happen, not in protocol design. Protocol should be synthesized from specification. Okay? So that was one of the big pitches of that work. Now, again, in the spirit of parallel lecturing, here's how I do it in Bloom. All right. So in Bloom, and this is just a thought, so tell me if you think this is nuts, but the way that we do distribution is by default, tables are a single node construct, and you declare your tables like this, link and path and best. Tables can have keys and there we go. And then I'll have another type of collection called channel. And in channels, I'll specify which index of this array is the location specifier. To the programmer, a channel is a place where you stick facts, and they pop out at the address in the second field. So to a programmer, it's like, where's the address in this packet header? It's in the second field, or the first field, or whatever. So I think this feels really operational, but it's exactly what I did on the previous slide. It's just a relation, okay, that's partitioned in a particular way. All right? And once you do this, the program is pretty straightforward. There's one little syntactic addition here, is this operator. I'm forcing the programmer to write down when their sticking is going to be asynchronous. All right? So if the thing on the left-hand side is a channel, I'm going to double check, and this is syntactically redundant, you don't need this, but I'm going to make the programmer say less than plus. And then in their face, they know that this happens atomically. The minute you know this, at the very same time you know that. This happens asynchronously. I don't know when that's going to happen, sometime in the future. Okay? And if time permits, we'll talk about why that's logically interesting. All right? But from a programmer point of view, it's nice to separate local computation from distributed computation and asynchronous computation. Really important. So far, what do we got? Well, cool. We have actually a distributed logic now for implementing protocols. We find ever better paths. The thing that you should be suspicious of, if you're a PL person or a distributed systems person, is I've said nothing about all the hard stuff. Where's the concurrency stuff? What do I do about updates and the ordering of updates? Right? Isn't that all the hard things I learned about in my distributed programming class? And threads and locks, and where is all that stuff? And what about replication? A big deal in a lot of these systems is you have caches, right? And the caches are out of sync. And when does that matter and when doesn't it matter? And the typical answer to those questions, if you're a logic-y kind of language, is, all right, we're not going to be fully declarative. We're going to stick in some imperative stuff. All right, so in SQL and in our language overlog that we did our routing stuff in, and in, for example, the IBM work on Reactor, what you do is you have an iteration of declarative stuff followed by install the facts in a database, and then start over. And so there's this kind of cycle of state mutation with little pieces of logic inside of it. But this is terrible, because then the program has to reason about when do their deductions become visible in the database, and how does that affect future deductions. And it led us to lots of headaches. I mean, this is my pain I'm expressing. I'm not criticizing other people. I'm criticizing myself in the past. So how are we going to fix that? Well, we're going to have better logic. All right. So I'm going to quickly introduce you to Stephen Daedalus from James Joyce's Ulysses, and also Daedalus from Greek mythology. But actually, I'm just going to teach you a language. I like to play a game at this point in the talk. I'm trying to go fast because I'm running out of time. The game is good. The game is worth playing. It's called Disorderly Blackjack. Okay, so you have to be able to pass cards to your neighbors. So hopefully folks are close enough to, you can have a few, you can have a few, you can have a few, a couple for you guys. Here's how disorderly blackjack works. It's a very cooperative game. You get some cards. You try to form 21 out of the cards you have. If you have 21, raise your hand. Make a note to yourself of which cards formed your 21. And then pass your cards on. And eventually, the hope is you will get lots of 21s. And we can replicate. You know, it's OK if somebody computes the same 21 as somebody else. All right, and you got a joker, which won't do you much good. So pass cards. Those of you who didn't get cards hopefully will. And when you find 21, raise your hand, wave. OK, we got some blackjacks. Any amount, pass them around. It's all good. Okay? And as I like to say, a feature of this game for someone like me is you can play this game without a full deck. All right? So I don't know how many cards are actually out there. All right. Part of this, though, is a test of the audience. Can they listen to the talk and play at the same time? All right? All right. It's a fun game, yeah? So what is Daedalus? What is this logic? It's going to be plain old Datalog, for those of you who are Datalog people. But we'll introduce two new constructs. We have to introduce an infinite relation. Remember, we had an infinite relation before. This one is the successor relation. I need the successor relation. So what you would expect, 4, 5, 5, 6. You guys are failing my test. Parallel, game, and talk. Come on. So I need a successor relation. I will need stratified negation, the way I described. All right. And then we're going to do two stylistic things in this logic that are restrictions on Datalog in some sense. Every predicate is going to have a final attribute called timestamp, or T. It has no meaning because it's just Datalog. It's just syntax. But everybody predicate's got to have this.
We're cheating.
That's not cheating at all. That's great. And the other thing is that because everybody will have this final timestamp, we'll unify on that timestamp in all our rules. So you'll see this. This is a Turing-complete language. It has no operational semantics. So here's what Daedalus looks like unsweetened. It has three kinds of rules, OK? It has what we call deductive rules, which are plain old Datalog. And there you see the T in the right-hand side of every predicate. All right? And this just says if x is in q at time t, then x is in p at time t. And you can think of that at time t if you like in that way, or you can just say symbol matching. The t field has to match the t field. Okay? So facts will be true if they're coeval. Yeah? All right, a second thing we're going to have is induction in time. So we'll allow inductive rules. This says if x is in q at time t, and u is the immediate successor of t, then x is in p at time u. Okay, so you're allowed to put things one step into the future if you want to think of it in those terms. And then finally, for distributed systems, we need asynchronous rules, which say if x is in q at times t at time t, then for some time z, which is uniquely chosen for each xt pair, x is in p at that time z. And this is chosen uniquely and non-deterministically. And this is done using a little trick with a cycle through negation in the logic that we stole from Greco and Zaniolo, which I'm not going to go into. All right, but there's a reasonable interpretation of this as a committed but non-deterministic choice of a value. All right, so among all possible z's, we'll pick exactly one, and we'll sort of remember it. It's a non-deterministic coin flip for z. Okay, so that's what asynchrony says. Any questions?
Does Z remember the rule that it came by, or?
It doesn't carry it by default. It doesn't carry it by default, but the semantics are that it's committed. So it's not a disjunctive logic where you keep two truths, two possible times in your head at the same and juggle them. We're going to have just one. Okay, so there's only one possible world. And if you like a little syntactic sugar, deductive rules, we can drop the t's because they're implicit. Inductive rules, rather than the t in the successor, we could just say at next. And asynchronous rules, rather than all that crazy choice stuff, we could say at async. We actually started writing programs like this, but even this is still kind of yucky. All right, let's look at a little program. And my point here is that we can do stateful computation now. All that stuff that I got rid of, the last 10%, was about updating state. So can I update state? Well, how about a flip-flop gate? If I can do a flip-flop, then I can do a memory, right? So how do you do flip-flop? Well, we'll have a relation called bit. And at time 1, I'll insert a fact flip. Or if you like, in the unsweetened syntax, this is flip, comma 1, right? And I'll have a rule that says if flip is in bit, then flop is in toggle, some predicate toggle, which is derived from bit. And if flop is in bit, then flip is in toggle. Those are rules. And now I can say something like, if you're in toggle now, you're in bit at the next time step. So that's a flip-flop. Starts out as 1, then at 2 it's flip, at 2 it's flop, at 3 it's flip, at 4 it's flop. Okay? It's not exactly a flip-flop. It's actually a trace of a flip-flop over all time. Okay? But that's OK. Nothing wrong with that. All time exists at the same time. It's fine. Time is just a marker you put on things, right? Okay, and in Bloom it looks like this. Rather than calling these things tables, we're going to call them scratch tables, because I want them to delete themselves at every time step. At every time step, they'll be empty. Because after all, in Daedalus, we had the T field. The T field said what time you mean. Here we don't have the T field, which means facts don't persist from one time step to the next. They'd sort of evaporate if you forget all the history. So scratch table is true only for one time step, and then it's forgotten. All right, and here we have bit is a scratch, toggle is a scratch. For everything in bit, if it's a flip, return flop, else return flip, and stick that in toggle. If something's in toggle, and now this syntax with a scratch at the left side means in the very next time step, put it in bit. This is an at next type of rule. And this is a flip-flop in Bloom. Once I inject scratch in at any given time. Sorry, a bit into that scratch at any given time. Okay? So how do you do persistence in Bloom? What is, or rather in Daedalus, how do you do persistence in Daedalus if a fact is only true for one time step? It's ephemeral. Well, you do it by being persistent, you see. So persistent people just keep trying, right? So this is how you do persistence. You just write a rule that says something like, if you're the mayor of a city if you, Mr. Y, are a mayor of city X, then you'll be that at the next time step. All right? So inductively, Mayor Daley is the mayor forever. Okay? Close to true. All right, but this isn't often what we want. We often want to be able to do updates and rewrites and deletions and things like that. So let's do updatable storage. For updatable storage, we need to introduce a little bit more to our persistence rule. We'll say y is the governor of x, and y is not in the delete governor of x, then y is in the governor of x at the next time step. So Blagojevich is governor in 2003. In 2008, we insert him in the delete relation, such that at 2009, this induction is broken. He's not in the relation as of 2009. And by the way, atomically, Quinn is. Okay? So that's how we do deletion. And what it says is that persistence is merely the induction of something that keeps going until the induction is broken. Okay? And that's a logical way to think about state modification. Okay. And in Bloom, we don't write it like that because that's annoying. We just say T is a table. And we have a deletion operation, which is the same as inserting something into the del version of the predicate. So this is the same as saying, put this tuple into T del and have a persistence rule with that T del. But nobody wants to program like that, so we'll just call it delete. And I'm doing that as less than minus. Okay? So this method puts Blagojevich in. This method impeaches him. And these are atomic. These happen at the same immediate time step transition. Right? There's no time at which those two facts are somehow racing. So I've shown you Bloom. Bloom is a language with three main collection types that I've discussed: scratch, table, and channel. You can build others from these. It has these simple methods on collections that most of which were already in Ruby. So map and join. I had to implement join. Reduce, group, arg, ag. Those are all kind of the same aggregation methods. And then these three main operations: deduction, induction, which is one step for scratches and tables and asynchronous for channels, and deletion, which is this induction breaker, but you don't have to know about that, right? And then, if you want to write some side effect Ruby and toss it in the mix to do arithmetic or other things, please feel free, because I have the Ruby interpreter there. So we have lots of convenience libraries available to you. Okay, so that's the end of my language primer, and I'm sort of out of time, but I have time to talk briefly about these implications. But first, we have to end the game. Okay, so the winner of disorderly blackjack is the person who got the most blackjacks, most distinct blackjacks. So who is that person? Which one of you guys got the most blackjacks? How will we figure out who got the most blackjacks? Somebody propose an algorithm for computing the person who got the most blackjacks.
So ask the person with the largest number to hold up the same.
Excellent. Wait a second. That's called declaring the winner. So we could do this. We could do search. We could broadcast. Anybody got more than 5? Anybody got more than 7, right? We could do search. But we'd have to do search on this broadcast channel, right? Bottom line is that to do it, we're going to need to communicate or coordinate, if you like. Okay? You can't individually declare yourself the winner without knowing what other people got. All right? And a similar but more interesting question, how many ways were there to win? Which is maybe what the collective of you was trying to compute for me. Thank you very much. In order to actually get that, I have to write down all the blackjacks you found. And even that's not enough, right? I have to enumerate all the things you didn't look at. So again, for these are counting queries. These are non-monotonic reasoning, and they required communication. And I tried to point out that the matching, the joining okay, the forming of collections that equal 21, that you did locally and you raised your hands as you went. There were data dependencies. You had to wait till you got the cards that gave you 21, but that happened monotonically. The counting is non-monotonic and it requires coordination. Okay? So counting waits, but waiting counts. So this distributed aggregation, how do you count in a group, especially if you have recursion? So this was really simple. We were just forming pairs. But if you're recursing through rules and you're building more complicated structures, how do you know that a message that's in flight isn't going to generate more facts? Okay, well, you need to have coordination. Even to determine that there's no answers, you need to have coordination. And so the way we do that is we have to wait. We have to wait for everybody to sign in with their results. Say, I haven't sent anything, and here's all the stuff I got. So now you know all the network channels are empty, and here's all the things you need to count. Go count them. Right, that requires some kind of waiting protocol. So how do waiting protocols work? Well, there's things like two-phase commit and Paxos and Byzantine fault tolerance, which you may have heard of. And all of these entail some sort of voting scheme. So this is a unanimous vote scheme. This is a majority vote scheme. There's a two-thirds majority vote scheme. What's voting? Voting is counting. So counting requires waiting, but waiting is a counting protocol. This is good. So the COM conjecture, which is sort of there's a lemma in one direction and a conjecture in the other direction, is that logically monotonic programs and programs with distributed coordination are the same set of programs. I'm sorry, and programs without distributed coordination are the same set of programs. And that if you have non-monotonicity, you were required to use a coordination protocol. So this awaits a really crisp definition of coordination and a crisp definition of consistency. Okay, but in one direction, at least, it's easy to show that monotonic programs are confluent. So the facts can arrive in any order, and they produce the same outcome. So I know for monotonic programs, I don't need coordination. The other direction is quite a bit subtler, but if you want, I can talk about it later on. And this is a big deal in the distributed systems community. Eventual consistency is a buzz phrase they like to toss around. They often don't define what it means very well, but it's something they would like. All right, and I don't have enough time to go through it. Instead, what I'm going to do is, in this crowd, I think the last thing to do is talk a little bit, again, about something I've been leaving out. So if you're a distributed systems person and you publish in the PODC conference, Principles of Distributed Computing, you will certainly know Leslie Lamport's famous paper about clocks. So distributed clocks is sort of the foundational paper in PODC. Okay? And it talks about the clock condition that makes distributed computers make sense with each other. And it says if you have a partial order at one node of things that happened before other things at this node, and you have clock identifiers assigned to those, and at some other node you have some things that happen before each other, you have clock identifiers assigned for those. For any events A and B such that you can prove that A preceded B in the partial order happens before, including message passing being one of the things that happens, then the clocks had better respect that order as well. All right? So it better be the case that your clocks respect the partial order of events in your system. Otherwise, your system doesn't make sense. You don't really have distributed clocks. Okay, and that's very nice. Except, you know, Leslie Lamport, he's a grouchy old guy, and he's telling me to do things his way, and he's asking me to respect the order, and it's his grisly rigor, and I don't like it. I'm disorderly. So for the undergrads in the room, it's like, you know, don't listen to these guys. You know, you don't have to do what Leslie Lamport says. So if you ask me, time is for suckers, okay? So time is, well, it's for non-monotonic suckers anyway. So here's the deal. Time flies like an arrow. This is Groucho Marx. Time flies like an arrow. Fruit flies like a banana. No. This is actually the point I wanted to make. All right. Who says we can't go backwards in time? Who dares to say to me that I cannot do time travel? I mean, come on. So here's one I used at the PODS conference, database theory conference. Here's a rule, makes perfect sense to me. If you publish a paper in PODS, you're a theoretician. When did you become a theoretician? I don't know. Maybe when you were born. Maybe you were born a theoretician. If you publish in PODS, it means you are a born theoretician. That makes perfect sense to me. Right? Does this say that the PODS program committee sent mail into the past to your parents at the moment of your birth that arrived, like paper acceptance or a badge? No. Okay, that's silly. But it still might be the case that the fact that you're a theoretician should be a fact at the time of your birth so that you could use it for other computations. Why not, right? Well, okay. If you're an AI person and you like sci-fi, which is a bad combination, they have these things called temporal paradoxes, like the grandfather paradox. The grandfather paradox is one of these things, you know, it's like a bad old TV episode where you go back in time, because you can, because I just said you could, right? And you kill your grandfather before your father is born. Whoa, but that means you don't exist. Well, that means you couldn't have killed your grandfather, which means you exist, which means you could have gone back in time and killed your Wow, that's so cool, right? That sci-fi is so cool. So let's figure out what that's trying to say. Let's do it in Datalog. All right. So, and I know some of you have to leave, and I'm almost done, but for those of you who have to go, I apologize. We have a triple has baby. So x and y have a baby z means x is a parent of z. It also means y is a parent of z. And if this is persistence of parent, which is a pattern we saw before. If you were a parent once, you're a parent until you're deleted. Okay? And if you're a parent, you've got the whole ancestor business going before you. Okay, we did that too. So putting all the pieces together. Now, if y mistreats x, then x will someday kill y. Maybe in the past. Okay? Because I didn't say you couldn't. All right? This is grandfather paradox. All right? And if you're in the kill relation, then I'm going to put you in del p. I'm going to take you out of the parent relation, because obviously if you're dead, you can't be a parent. All right? And why is this a paradox? It's exactly a paradox because of the cycle from parent through del p, through kill to mistreat, back to parent. I don't know if I actually closed the loop in the syntax, but the point is, crap. There's a cycle through this negation. Parent depends on itself through a negated predicate. All right, so if you draw the graph of predicate dependencies here, you'll have a cycle with a negation. And it's well known that that's meaningless because it reduces to p if not p. And so your really cool sci-fi story is like 1 if 0, 0 if 1. That's a really dumb sci-fi story, OK? Because it's just like logical inconsistency. Neat, right? And you say, well, yeah, if you think so. Yeah, sci-fi's kind of stupid. But the point is that murder is non-monotonic, OK? And the other thing you can take from that, the other side of the calm conjecture, is you can indeed go back in time and impregnate your ancestors, and that is perfectly consistent. Okay. So I will close with that. There's a bunch of other conjectures, but I wanted to leave you on a high note, so the last thing I need to do is just thank my collaborators, because a lot of this was systems work, and there's been just a whole bunch of people we've been working with. Yahoo Research has been a very tight collaborator over the last many years. The work started when I was running the Intel lab at Berkeley, so some of that work was reflected here. Yeah, we've had a lot of help and a lot of fun. So I wrote this stuff up sort of in the style of this lecture, if you can imagine, in a little paper, so you can read that too if you like. Sorry to run over. Thank you.